But even assembly language can stand some improvement, which brings us to the final evolutionary improvement in computing languages, high-level languages. High-level languages are the ones you may already be familiar with, such as Java, C or C++, JavaScript, Python, and so forth. They are highly symbolic and much more English-like, which makes them far easier to develop in than either machine or assembly language. In high-level languages, such as Java, single human-friendly statements replace multiple lines of assembly or machine language. However, as this diagram on the right shows, it's important to recognize that the underlying assembly and machine languages haven't gone away. They're still there, just buried under the hood now. CPUs can still only understand these underlying ones and zeros of machine language. We've just added a few intervening layers to simplify matters. High-level languages are usually portable between different CPUs, or at least mostly so with only minor tweaks. Another program called the compiler turns a program written in a high-level language into the equivalent assembly and then ultimately machine language. All of this is done easily and repeatably, which is why we seldom have to concern ourselves with the underlying assembly or machine language anymore. High-level languages can be classified as compiled, interpreted, or hybrid, which means some of both, as is Java. We'll see what this means a bit later on. Hundreds and hundreds of high-level languages have been developed over the years. Some ones are probably familiar to you. Countless others you've probably never heard of. If you'd like to get an idea of the breadth of programming languages out there, try Googling high-level languages list or take a look at the Wikipedia link in this week's lecture module. Here are a number of examples of various high-level languages. All languages have their individual strengths and weaknesses, and some are better suited to certain types of problems than are others. You're probably familiar with many of these names already. I've tried to list the ones taught at this college toward the top of the list. Our current focus, of course, will be on Java, which is a solid choice for general-purpose applications. Java, by the way, is the programming language used in Android application development. But you can see lots of other familiar ones in this list. C, C++, Objective-C, PHP, Perl, JavaScript, etc. As you can see from this list, many of these languages are most commonly associated with certain types of programming applications. The perception, real or imaginary, that a language lacks certain features can often be a driver in the development of new languages. Again, if you're curious, here is the same URL that is posted in this week's Canvas module. Here's a bit more historical perspective on the lineage of high-level languages. Smalltalk, in the middle 1970s, is generally considered to be the first object-oriented language. C, dating back to the early 1970s, is the development language underlying Unix. C++ originated in the early 1980s and is often considered as C with objects. It's syntactically very similar to C, but it also added lots of complexity. Java, of course, is the language that we are interested in. It was originated in 1995 at Sun Microsystems, and they originally wanted to call it Oak, but I guess that name was already taken. Oddly enough, it's said that the alternate name Java came about after a visit to a coffee shop. Sun Microsystems was acquired by Oracle in 2010, and they obtained all the rights to Java. So as of today, Oracle maintains and develops Java, but you probably already knew that if you've tried to download and install the Java JDK. We said a couple slides ago that high-level languages could be further classified into three general types: compiled, interpreted, and hybrid. Here's a short overview of what each type means. In a compiled language, a compiler converts high-level language source code ahead of time into the native ones and zeros of machine language that can then be executed on a CPU. Some examples of compiled languages are C and its variants, such as C++ and Objective-C, which is used for iPhone apps. Compiled languages tend to run very quickly on a processor. In an interpreted language, an interpreter still converts high-level source code into native ones and zeros, but now this conversion takes place line by line at runtime, not ahead of time. Some examples of interpreted languages are PHP, JavaScript, and Python. Interpreted languages generally run somewhat more slowly than would a compiled program. Java is a hybrid language, which means that Java source code is still compiled ahead of time into what we call bytecode, and then that bytecode is executed at runtime by the JVM, or Java Virtual Machine. We can think of that bytecode as Java's executable, except that it's now runnable on any JVM, which helps solve the problem of platform dependence. What exactly do we mean by that? Here's a picture of what we mean by the problem of platform dependence. Let's say we had some software application written in some earlier high-level language. That would be represented by these boxes at the top, which are all different shades of blue. Our source code might be substantially the same, but usually there are some slight variations owing to the specifics of these different platforms. And by the way, when we say platform, what we mean is some specific operating system processor combination. So each platform requires its source code to be compiled using a different compiler, which results in 3 different platform-dependent executables, one for each different platform. The Platform 1 executable can only run on Platform 1. It cannot run on Platform 2 nor on Platform 3. And the same is true for the other 2 executables. So we started with one body of source code, but due to some small platform-specific differences, that code resulted in 3 different executable programs, one per platform. This is the platform dependence problem, and from my own experience of supporting software across multiple platforms, this problem is a real nightmare from a support standpoint. We will leave it at that for this topic, and in the next lecture segment, we'll see how Java solves the problem of platform dependence, making it such a popular language for development. See you there.